Good evening. I'd like to welcome you all to the last in our series of webinars around climate responsive retrofit. So this is in part of our Interdisciplinary University Challenge 2023, and tonight we are all about getting into the details. Now, if my slides will move forward. So a huge challenge. Retrofit is going to be so essential. It's not easy, it's far more challenging than new builds, and it takes a team of knowledgeable, caring professionals to do schemes that work. We need our future professionals to understand the complexity and embrace the constraints and challenges. Timber Development UK, in partnership with the AECB, Beth, Enmite, Edinburgh Napier and the Passive House Trust bring you this challenge, and we are bringing you software from Trimble, Passive House Institute and the AECB. So what we are asking is you to form interdisciplinary university teams to design, engineer and cost a retrofit scheme for an existing timber frame building that requires a second life. And it's the old cricket pavilion in Hereford. And tonight I'd like to introduce you to our speakers. So Gervase Mangwana from Waxwing Energy, Florence Collier from Humblebee, and Beth Williams from the Build Collective. And with that, I'd like to hand over to Gervase. I'm going to stop sharing. And I know Gervase has got to leave us early tonight. So if you have any questions, please pop them in the chat or the question and answers, and he'll answer them before he goes. All yours, Gervase.
Has that worked?
It has.
Great. So yeah, I'm just going to rattle through. I'm going to kind of assume that you don't have great existing knowledge about air tightness and air testing. So excuse me if that's a big assumption. So I'm just going to run through a little bit about what air tightness is, why it's important, how we test, what the regulations and the standards are, and then some stuff on retrofit and some stuff related specifically to the cricket pavilion, which we tested a couple of weeks ago. And now it doesn't work. It does. So yeah, we famously say in retrofit and also actually in new build now, build tight and ventilate right. What that means is that we want to get the fabric of the building as tight as we possibly can, as close to no leaks as possible, really. And then in order to keep the building healthy and the occupants healthy, we ventilate appropriately, and Flo will be talking to you about that a little bit later. It's also important. It's important because of the heat loss from infiltration. So when it's windy outside and there's pressure differences across the house, then through all the holes in a property, the heat leaks out, and I'm sure you're all familiar with drafts, and that affects comfort. The sort of hidden thing that it affects is structural integrity. So where warm, moist air is leaving a building through a hole in it, at some point through the fabric, it can become a lot colder and condense, and over time that can lead to kind of hidden rot and other sort of structural problems associated with moisture. In a design process, it's important to specify and design in an air tightness layer so that everybody's clear about what the strategy is, where it is on the sections, and so that the builders, when they come to look at it, should they look at the drawings, can clearly see how they're going to build it. It does require a lot of attention to detail. It doesn't really cost a lot more money to do it. It's a small amount of extra money really to detail in and cost in with the tapes and the membranes as a proportion of a build, but it does require a good level of attention to detail and care in order to deliver and get the best out of the extra cost of the materials. It's quite easy to just buy the materials and still end up with a bad result because it's not been implemented properly. And it needs all trades to buy in. So on top of that, even if you've put a amazing air tightness barrier. If the electrician and the plumber didn't know about that, then they'll merrily go around punching holes back into it afterwards. And traditionally, until recently, in order to test buildings, we do that with a blower door, as a picture of there on the right hand side. We blow air in or suck air out of a house, try and maintain a pressure difference of 50 pascals between inside and outside, and measure the flow that results from that. And via a couple of different methods, that gives us a metric of how leaky a building might be. Typically in the UK, it's only really required for new build, and that test is done at completion. Unfortunately, that's at the point where it's no longer possible to do anything about it. So in low energy building, we tend to use diagnostic tests, sometimes before, in the case of retrofit, sometimes beforehand, but almost always during the process where the air tightness layer is still visible and it's possible to rectify any problems with it. Just quickly, because you're going to, if you get into air tightness, you'll hear about two different metrics. In the UK, we use permeability as the measure for measuring how airtight our buildings are, and that is measured as that flow, meters cubed per meters squared. Sorry, meters cubed per hour flow that is required to maintain 50 pascals in the building, divided by the surface area of the building, meters squared in meters squared. Whereas air changes per hour, which is used in the passive house standards, is by a reduced or useful volume inside the property. That gives you the air changes per hour. And for normal buildings, for sort of normal sized, normal shaped buildings, they're often actually very similar. But in complex buildings, or very large or very small buildings, they start to drift. And you can sort of see the example there on the right hand side, that the surface to volume ratio of those three different cubes with 3 meter, 6 meter and 12 meter sides is there's a fourfold difference between the top and the bottom of those. So yeah, air changes per hour actually punishes very small buildings and single story buildings. And permeability is actually a more useful representation of how leaky a building is, because it's actually through the surface area that the air leaks. In terms of heat loss, it's air changes per hour is a better measure, because that is the volume of heat that is leaving. The regulations we have at the moment in the UK, SAP has a backstop of 8 meters cubed. It's just come down from 10, although almost all SAP built houses have the notional house is 5 meters cubed. Passive house has 0.6 air changes per hour. So yeah, again, for a normal place, you'd sort of imagine that the permeability and the air changes are similar. So you can see that there's almost a 10-fold difference between what is a normal new build house in this country and what a passive house would expect to be. The AECB new build standard is relaxed from there at 1.5 air changes per hour. Retrofit, the retrofit standard that would be relevant to you, is a little bit relaxed from the passive house standard at 1 air change an hour. The AECB, the new AECB level 1 and level 2 retrofit standards. The level 2, the deep retrofit, is that we've switched back to permeability because of the reasons I outlined just before. The level 2 is at 2 meters cubed, so it's still quite a challenge, but not as challenging as the new build or anywhere near as challenging as Retrofit. And the level 1 we've put at 5 meters cubed. So the level 1 is the heat pump only standard for those of you who are on the call last week. And we deemed that the right level because for very light retrofits, it's actually really hard to make big improvements to the air tightness. Air tightness in retrofit is actually unregulated, except I think the new build regs, the new regs that came in this year did require extensions to be tested somehow, although it's not yet clear how that's possible, given that most extensions are kind of open to the home that they were extended onto. Retrofit is much harder to treat. It's very hard to do at scale without getting people out. Yet the implications are similar. So all the stuff that's beneficial in new build for good airtight buildings is still very true of retrofitted buildings. And those of us who are kind of facing heavy bills this winter will air tightness would be a big factor on that, as long as ventilation is considered along with it. The detailing is extra important because it's much harder to do. So, and there tends to be more, it's very easy in new build to design out or design in good and simple air tightness details. In retrofit, you're working with some things that you can't change, and therefore detailing them in a sort of simple and buildable way, it becomes sort of more important. And often this stuff actually doesn't start to play out until you've started taking the building apart a little bit, and you can really find out where it is. But again, that strategy is important, choosing where you're going to have your air tightness layer. It can be on the inside, it can be on the outside. Sometimes if you do one, you end up doing one in some places and another in the other places, and where those two things join, as you can see, that can be a bit of a challenge. It really needs thinking about and some discussion with a builder. So I call the pavilion Wide Marsh. It's on Wide Marsh Common, so I know it is Wide Marsh because it's just down the road from me. We tested it a couple of weeks ago, and the permeability was 8.3 meters cubed per meter squared per hour. The air changes were 9.4. And what that kind of shows you there, the fact that the air changes per hour is kind of over 10% more than the permeability, is that the building, which you can see a kind of picture of the envelope down on the bottom right hand side there, has a high surface to area to volume ratio. And that obviously, having a lot of surface area where the air actually leaks through, makes it harder to get the air tightness down. The problems that we found really were particularly around the doors, which will be changed, and all of them were. You could see the gaps around the doors, couldn't you, Tabitha? It wasn't hard. We did actually have a go at taping some of them up, I think, actually. So this test wasn't a kind of true representation of how bad the building is at the moment, but some of them we couldn't get to. There was quite a lot of stuff in the way. The windows, the single glazed timber windows, they were also pretty bad. But yeah, one of those kind of hidden ones that you don't expect to see, and I see this all the time in new builds as well, leaking through sockets. So somehow chasing of cables and putting in of sockets has not been done in congruence with the air tightness layer, and therefore that is a leakage point. My recommendation would be to ensure that the extensions, you're aiming at the extensions to be as airtight as you might a passive house new build, because it's really not that hard to do. If simply detailed, and the materials are, like I say, aren't that expensive. And overall, if you're extending the building, you'll be removing some of the existing elements, putting in new, very airtight elements that will help to bring the overall air tightness of the building down. Strongly recommend that you would have a retest done at some point while the air tightness layer is still visible and can be rectified. And I think it's a really good idea to choose a target, to be ambitious, and then smash it. It's really good to get everybody involved, the designers and the builders, to get them engaged about what the target means. And then everybody likes a little bit of a competition. Usually there's a good gathering around the air tightness result as it comes in, and everybody's keen to know what it is. Sometimes it's disappointing, but if it's done at that interim stage, then there's a motivation for people. They've often heard of or been involved in another job which did better or worse, and so having a target, something to aim at, having the opportunity to improve it and retest it and prove that your retesting has been successful is really good exercise for designers and builders alike, if we're to sort of widen the skills of good airtight retrofit going forward, as we need for the rest of our building stock across the country. That's pretty much all I've got. So if anybody's got any questions, I'm here to take them.
So you're welcome to put them in the chat, or I don't know if Florence or Beth have got any questions, just so that you don't disappear.
It's very quick, wasn't it?
Yeah, precise to the point.
That's great, Gervase. Thank you.
You're very welcome.
And thanks for updating me on the AECB standards, because I was still at 2.5 air changes.
Oh, right, yeah. Yeah. And we have switched the retrofit standards to permeability now. And there's a discussion about whether they're going to do that in the new build standard as well. In fact, I think they probably are, because they've just decided it'd be too confusing
Yeah.
to have different standards. And we're trying to lobby the Passive House Institute to change to permeability as well, because of that thing that it favors very large buildings basically, and that's not really something that we want to do, and it punishes very small buildings. So in some ways that's, you know, it's just a lot harder to meet a target if you've got a very small building. So with tiny houses, it's almost impossible to meet. You know, although that said, I test for a few passive house builders around here. They're very intercompetitive, and they both regularly get somewhere around 0.1 air changes per hour. So yeah, it's really not that difficult to achieve 0.6 in most cases.
Hereford is a hot spot, as is Durham, I think.
Yeah.
We have a question from Deepak. Hi, Deepak. Lovely to have you here. And he's saying, sorry, still a bit confused. Is meter cube per hour from building regs the same as passive house air changes per hour?
No, it's not. And sorry, I've gone through that very quickly. So it's meters cubed per meter squared hour for the building regs. And so when we're running the fan, the information that we get from the software in the fan is a flow rate. So that is meters cubed per hour of air that is leaving or entering the building. And then we use that flow rate, and we can either divide it by the surface area of the house in meters squared, and that gives us the permeability that we use for building regulations, or we can divide it by the volume of the house in meters cubed, and that just gives you 1/hours, which is air changes per hour, which they use for passive house. But it is worth pointing out that passive house, they make you measure the actual volume of air in the actual room. So you take out all the walls, all the, you know, all the interfloor, yeah, chimney breasts, so forth. So it really is a kind of reduced volume to represent what actual air is in the building. So it does make it sort of as hard as possible, if you like. Hope that clears that up.
Definitely want you to have a whiteboard and drawing on it at the same time. Explaining. No, really appreciated, Gervase. Thank you very much.
Well, yeah, I hope you have a successful rest of the webinar. Cheers.
Bye,
Thank you. Are you? Yes, please.
Yeah.
Yeah.
Is that working? Yeah. Well, good evening, everyone. I'm Florence Collier. I'm a mechanical engineer in building services, and I set up Humblebee about 4 years ago. I'm also a passive house designer and a member of the ACB. And we recently completed phase 1 of our whole house retrofit, which you can see completed there. And I've blogged about it. I will post a new one soon with some data. So do go to the website and look at the blog. It's got costings in there as well, so that should help. It might be a bit out of date though with everything that's happening at the moment. We also founded the Positive Collective, where we looked into sort of timber buildings in quite some detail for a competition and came up with Positive House. So a lot of the considerations of timber we've looked at in detail for the building services in particular. And this is just a quick run through of what Gervase was going on about. You can, I don't know if you can see the red line, but in a new build you would try and draw this as a continuous red line around the section in all directions, and make sure that any details kept that sort of continuity intact. And for passive house, you'd be aiming for a smaller figure. But in retrofit, you are very much constrained by the existing structure, and you'll have sort of junctions and thermal bridges and all those sort of points of weakness that are really quite hard to treat. So yeah, ignore that 2.5 air changes. That's the old AECB standard. So Gervase is more up to date. And this graph just sort of illustrates what the impact of the leakiness has on the heat losses. So if you look at the notional building regulations building at 5 air changes per hour, this is the contribution of the heat loss due to infiltration. I mean, it is a bit arbitrary in one sense, in that it very much depends on sort of wind pressures outside, whether you actually get that infiltration in, but we have to quantify it in some way. And at some point you will get that amount, you will get a certain amount of air that's taken into account into the heat loss calculation. Your current building that you're looking at is nearly double that. So if you think about all this being a contribution from the infiltration, you can quickly see how your heating element gets very, very large. And down at Retrofit, then you can reduce that right down to this portion here, which is similar to ventilation. And this is ventilation that has heat recovery. And so if you didn't have ventilation and only extract, and I'm pretty sure the ACB standard allows you to have extract only, then that would be a large portion as well, because we're covering nearly 75% of that heat. Yeah, so that was just to say, so as you sort of close up the building, and infiltration is in places that you don't necessarily want it to be in, or you can't guarantee you have them in the right places. So the idea is to reduce the heat loss as much as possible by sealing the building, but that does mean that you will need to ventilate in order to keep things fresh, keep the materials intact, and prevent mold and growth and those kinds of things, and sort of hygiene issues. So this is what we're going to talk about mainly, is the mechanical ventilation. Like I said, you can have extract only as long as it's continuous if you're going through the ACB standard, but ideally you'd go for heat recovery, because all that air that you're sort of sucking out of the building, it has to come in from the outside, which is air that will have to heat up. So if you can recover some of that heat before you throw it out, then you're doing far better in terms of your energy standard. So essentially it's a machine with 2 fans and a heat exchanger, and the air comes in from outside. It's fresh, it's filtered, it's supplied, well, in a house it would be supplied to the living spaces and the bedrooms, and it would be extracted from the wet room, so you get rid of moisture at source. And before you throw that air out, you exchange the heat between the two streams. So the air coming in, instead of being 5 degrees as it is right now, or 3 degrees, it comes in close to room temperature, or at least not that far up. So much more pleasant to have in the house. As well as saving energy. And the other important thing about the MVHR is, so cold air can hold a very small amount of heat. If you bring that in constantly, a small amount of moisture, sorry, if you bring that in constantly, then you're heating that air up, you automatically lower the relative humidity in the space. So that's super important, especially if you've got some natural materials going on and you want to avoid condensation and moisture problems. So that's the other advantage. It works in the summer as well. You can recover cool as well as heat, so that's becoming increasingly a concern for people. Now, just looking at the building, you're likely to be using the loft space. I have to say, we have put our units in the loft. We're feeling the disadvantage of having done that because it is showing quite a bit of heat loss. So we are intending to sort of insulate more the actual unit itself. But if you can put it within the thermal envelope of the building, then your performance is much more guaranteed. But essentially, the unit goes up in a space. It has connections to outside, which are the intakes and exhausts. Now, if it's within the thermal envelope, then the intakes and exhausts are insulated, and the rest of the distribution is uninsulated. If it's outside of the thermal envelope, then you would not necessarily bother insulating the intake and exhaust, but you would insulate the portion of supply and extracts that runs in that loft space or that unheated space. Two different types of insulation, but I won't go into that. And then there are two ways of distributing, essentially. So you can either have sort of rigid ductwork, and it's called a branch layout. So you have larger diameter ducts that branch off the unit, and then you sort of branch off into smaller ones, and you need the crosstalk attenuators between spaces so you don't have transmission of noise. Or you could go for what's called the radial layout, or sometimes octopus layout. And basically the supply and the extracts are fed through a large manifold, off which you have these semi-rigid sort of plastic pipes, and they're quite small diameter, so you can thread them through to different spaces. That works pretty well in retrofit, because you can generally find routes for all of those, and you don't need the big attenuators in between. You will need attenuators for fan noise off each connection to the unit though. So this was our installation. That was Chris trying it on for size when it arrived. You've got so we decided to distribute quite minimally, but sort of in bulkheads mainly, and this was the existing bathroom riser that went down to the kitchen as well. So we just extended that boxing in the bathroom. You can see the extract valve here. The supply. This on the left here is the intake and exhaust. So it's a combined grill. So the exhaust goes through the middle of that grill here, and the intake is from the sides of that. Now, understanding the dimensions of these things is quite important, is if you want things to look nice. What you might not realize, because it looks like it's just perspective, but they did have to notch that notch that barge board to fit that on in the end, just because of the mess I made in terms of laying this all out. I got the handing of the unit wrong, basically, which is one of those things you can look at it for hours and still get it wrong. Yeah, so this is how I drew it, which looks very neat and doesn't take up much space. And this is what it actually looks like, pre-insulation. Right, so that was mechanical ventilation. I was just going to say another consideration in terms of the ventilation is because the pavilion might not be a dwelling, is that right? It's a sort of public use space. You may have compartment issues, fire compartments. I'm not entirely sure how big, well, it depends how big you're making it as well. So that will be a consideration in the routing of the ductwork. And also, in order to get transferred from the supply areas to the extract areas, we will need undercuts under the doors. But if they're fire doors, then we might need the ones with the intermittent linings at the bottom. So that's just a detail, but something to consider. And you might need sprinklers, or you might decide to have sprinklers. So, oh, I wasn't going to put that. Apologies for this, the both swearing, but yes. So I was just going to make a point about decarbonisation of the grid, and a lot of the calculations that we do assume this this red line here, which is the sort of steady progression decarbonisation, which doesn't actually get you there. So it's now called falling short, and we should really be doing something more like this, so deeper, sooner. And the only way to decarbonise your heating is to switch to an electricity-based form of heating. So that could be direct electric, but with the bills being what they are, and the fact that we need to decarbonise quickly, then I'm going to talk about heat pumps briefly, so that you have that as an option. How does a heat pump work? So you have got a heat pump in your house. It's called a fridge, which works in the exact opposite way of the heat pump. And it takes energy out of one source, and through a process of expansion and compression in the fridge cycle, it then releases that heat to your heat sink, which is in our case the building, or the water that circulates through the building. What was I going to say about this? Yes, so the air source heat pump extracts heat from air outside, ambient air, and the ground source would extract it from the ground. And the difference between the two is basically the ground source heat pump is easier to get higher efficiencies from, because the performance of the heat pump depends on the relative temperatures of the heat sink and the heat source. So how do we size the heat pump? We look at the U values of all the elements, the heat loss areas, and the difference in temperature between inside and out. So we have a design temperature. So I think Hereford is, I mean, the closest place is Cardiff. So the design temperature will be -3 in a bit. And you find the U value as a build-up from the materials of each of those elements. And their conductivity. And then you multiply that U value by the area of that element, and you top them all up, and you get the size of the heat pump for that particular building. So yeah, we talked about coefficient of performance, and basically what COP stands for is the amount of heat energy you get out of the system for the amount of energy that you put in. So COP of 4 means for every kilowatt hour of electricity you use, which is basically going into the compressor, then you get 4 kilowatt hours of heat energy. And this is just showing you how the COP varies depending on outside temperature. So an air source heat pump would need to be able to operate at much more fluctuating temperatures compared with the ground, so -5 maybe. And if you were to heat water, and you do need a hot water tank in order to do that, for large amounts of hot water, then your COP is actually not that great. So that's 1.5, so just 50% better than direct electric. Whereas a ground source heat pump that's feeding, say, underfloor heating, which is probably, so you can see the delta between the source temperature and the output temperature is much smaller when the COP is more at 4. Yes. Oh, and just on hot water, sorry, depending on the activities that are happening in this building. So if you have a kitchen, for example, you might want to consider a store, and you might want to be able to use the heat pump for that. If it's just bathrooms and it's hot water for the wash hand basins, you might consider just point of use electric heating, because that's just very efficient, and you'll be designing the heat pump more efficiently for the heating system and stuff. So then you just need to decide on the emitters, and you can design radiators to operate at low temperature, so you can go down to 35 degrees low temperature. They just need to be sized correctly, and you can only really do that if you've worked hard on the building fabric. If you're going for the AECB standard, you're most likely to need a high surface area, so underfloor heating would be a good option here. I don't know how I'm doing for time, but that is my last slide. So, is there anything else I was going to say about this? I don't think so. Oh, another option is air-to-air heat pumps. So you would just do away with the hot water system in any case, and you'd have like an air conditioning style arrangement with sort of wall-mounted units and blow the air. But that means refrigerant going between the outdoor unit and the indoor unit, which needs a specialist installer. But they're all specialist installers, so it doesn't really make much difference. It is actually a lot cheaper to do that if you can live with the aesthetic. So that's me, really.
So you're saying air to air is cheaper than, because of not having all the infrastructure of the radiators and
yes,
the water,
but also
and
it's for some reason it's something that installers find they've done for ages, because it's just an air conditioning system working in reverse. So yeah, I mean the cost for installing water heat pumps is phenomenal compared with when you think about how cheap air conditioning systems can be. So yeah, I've never really understood it, but there you go.
No, that's a really interesting thing. I'm sorry, asking the questions, because we are retrofitted, and I'm sure the students will learn this all the way through. And I didn't know what to do, and ended up putting electric underfloor heating in, so an electric mat. Oh, yeah. But I'm concerned that might go in the future. And I was thinking, okay, do I now put another electric mat on top and then put some more tiles on top? Or yeah, maybe an air to air is the way to go.
Yeah.
No, good tip. Thank you for that.
You're welcome.
Lesson. Yeah, you'll come and charge me for it. We have a question from Deepak. So for Passive House MVHR, do we supply air in the wet rooms as well, or is it only extract in the wet rooms?
You don't need to supply air in the wet rooms. No, you can extract all your air through that, but you do need to make sure it's balanced. So if you have a large amount of supply just because of the occupancy rates, you need to find more points of extract, perhaps, than you need just for the bathrooms. You can extract it all through the bathrooms, and if there's a kitchen, you can extract it through there. But then you might need like a grill through the door rather than undercuts. To get that.
So that's just because of the volume that you'll be needing to exchange, and trying to all pull it through one thing, you'll end up with a bit of a vortex that, yeah, and a bit noisy.
It will be, yeah,
yeah,
it will struggle.
yeah. So brilliant. Thank you for that, Florence. Any questions, please pop them in the question and answers, and I'm sure Florence will answer them. Yes.
Great. Oh, I've realised I've started halfway through my presentation. Let's go back to the start again. Here we go. Right. Let's make sure that I can still see you all, because that's always nice, isn't it? Right. Hello. Hello, everyone. Hopefully you can hear me okay. Is that all right? Good. I thought seeing as Florence was showing a picture of her retrofit, I'd add one of mine here. This is what I was just saying I've been doing this week, is air tightnessing around my new doors that I've just had installed, because we're doing a stage retrofit as well. So the doors were installed in the summer, and now that it's got cold, I've suddenly realised that I need to air tightness around the door. So a little picture in progress of what air tightness taping looks like going on there. But yes, I'm a structural engineer in my day job, and I'm a certified passive house designer as well, although I don't technically use that very much but basically I specialise in doing low energy and passive house buildings. If I can get this to move on. Hello. There we go. There's some little pretty pictures about what we do in a practice. There's a lot of small domestic, largest domestic projects, I guess. New build houses, lots of passive houses, and then retrofits as well. And if it retrofits, yeah, and that's sort of what we do. And then today I just wanted to go through a couple of things really about what we get involved in structural considerations in designing low energy houses. Specifically, because obviously physics is the same, so gravity still works on passive houses, although much to architects' disappointment. So the design of the main structure is the same as most engineers you'll be learning at university, but there's a few things that come into greater consideration when you're designing passive houses and retrofits than would necessarily be in a sort of standard building regulations building. So I thought we'll go through that, and then namely looking at thermal bridging, and then looking at air tightness, which we've been talking about a lot today. So that's good. Other people have explained it, so I can just jump in with the detail. So we'll start with thermal bridging, just to explain a little bit about what thermal bridges are. They're basically a point in the building fabric where the heat loss through that area of wall or point or line is less. The heat loss is greater than the rest of the wall or building planar element around it. So we look at U values, which you've probably heard of for planar elements of the building fabric. And then we look at what's called psi values for thermal bridges. So they tend to be lines or points. They come in a couple of different variations. Let me just get my notes up a little bit better. So yes, so they usually occur at either junctions between two different elements of planar of the building fabric. So either like floors to walls or walls to roofs, or any of those kind of things, or other junctions with sort of the sort of penetrations through the main fabric. So windows, doors, services coming in, and those kind of things where something's different about the build up to the rest of the surface around it. So you'll probably maybe know from university that U values are the heat loss in watts over that area, a meter squared area, and then divided by the difference in the temperature between the two, inside and outside. So the thermal bridges are measured in a similar way. They're but they are per linear meter or just per point, depending on whether you've got a line thermal bridge or a point thermal bridge. So thermal bridges only occur if you've got insulation, so because they're the difference between the heat loss of the area versus that little particular point of the surface. So uninsulated buildings don't have thermal bridges because the surfaces aren't any better than the junctions. But so thermal bridges become a bigger thing when you're looking at super insulated buildings like passive houses or NFITs. So you've got an image here on the screen of it. This is an uninsulated wall here that we're just starting off with, and we've got obviously the U value there that it's showing is the big sort of 2 value there. So we've got a lot of heat loss through the wall itself, and then the psi value is the dark orange section. So you've got a bit of a loss through the junction there, but comparative to the U value heat loss that we've lost through the wall, it's pretty insignificant. And then if we look at this we're looking at retrofit here. We're looking at external wall insulation, for example. So we're adding insulation on the outside of the structure here. And what they've done in the first image at the top there is they've left the little stone sills on the windows, and then they've just insulated up to them. They've put another covering strip over the top of the sill just to cover the insulation so that water doesn't get down the back. And then they've just left the window as is basically. So you can see that now that we've reduced the U value of the walls significantly, so that yellow section is very, very small, but we've increased the composition of the thermal bridge there at that same junction because of the relative difference between the two. So that becomes a significant portion of the heat loss in that area. Whereas looking at the same junction but detailed slightly differently, they've in the second picture down, they've cut off the edge of the stone sill on the face of the window there, and they've fixed a little section of high density insulation just to pick up the window on the outside. And then they've done the same external wall insulation. So the U value of the wall is the same between those two images, but we've significantly reduced the thermal bridge component of the heat loss there. And that is then down to where you can sort of see the psi value there is 0.02, I think, and technically for a thermal bridge free passive house junction it's 0.01, but so we're most of the way there. But you can see that just in the junctions there, in the details of that junction, you've made a significant difference to the performance of the thermal performance of that junction. And you can start to see how this becomes an issue when you're looking at structure. So obviously there we've got the structure, it's only supporting the window, but we've got some sort of structure there supporting some kind of building fabric element that's made a big difference to the performance of that area. And so then we look at things that in the structure that come into thermal bridges. We've got sort of typical steel frames going through the building on the left there. We've got things like with timber frames, people always say, oh yeah, we'll do timber frame and we can get rid of all the thermal bridging. There's quite a lot of steel work that goes into timber frame buildings, even in the best of times. So you've got things like a holding down strap there. You've got the really nasty catnick lintels that go in masonry buildings that go just a big plate of metal basically inside to outside. And then looking at retrofits, you've got the if you're doing internal wall insulation, that fourth picture along is the internal wall insulation, but you've got the floor joist, the structure running through into the existing masonry wall. So what are you going to do about those? There's all sorts of issues that come through that, moisture, but from a structural perspective, sort of needs to be there. But yeah, what are we going to do about that? In terms of thermal bridging. And then the final one is from the St Sidwell's Point. I nicked this off of a presentation somebody's doing, and it's a sort of incidental structure that you won't get involved in this project, but thinking about your future careers, this is the crane base that they needed for such a large project. They had a tower crane there. Those have massive, great concrete pads. So they planned very carefully out all of these pile caps with lovely insulated pile caps that they were going to come along and put their ground floor slab on. And then the temporary works engineer just come and plonked a massive great bit of concrete that was much higher than the concrete that they were doing for the pile caps and all of the rest of the concrete for the structure. So I was like, oh, that looks like a potential thermal bridge. And then they're asking the architects, they were like, yeah, we hadn't planned for this and we don't know what they're going to do about it. Yes, so well, they've got their passive house certification, so they must have done something with it, but I'll be interested to know what they did to get that out. But yeah, so things that you don't necessarily expect coming up in the structural design and influencing looking at time. Yes, so looking at that. So we'll just go through how I go about looking at thermal bridges in a building when I'm looking at that and attempting to try and sort of design them out or have chats with the architects about what we might do to design them out. This is just looking at this is actually a new build, but it could be a retrofit of a timber frame building. They're just a section of through what we've been doing. So I've marked out where the insulation goes. This is a good thing to do as a team. Theoretically, obviously the architect's in charge of where the insulation goes, but chatting together, this is the whole point of the multidisciplinary teams, talking together about where your insulation is going to go, where your structure is going to go in relation to that. So here we've got some of the structure in the pink zone, which is the timber frame with the insulation between it, and then we've also got some structure there in red, which is the steel frame, and then we've got the concrete foundation in green there, and you can see that the insulation is on the outside of the structure with the steel frame in some areas, and then it swaps to being on the inside of the structure on the foundation. We did want to put it on the outside, but then something about the architecture meant that we couldn't do an externally insulated raft in that instance. So we ended up, so we've got a swap there of where the insulation is in relation to the structure. So I'll draw that out in plans and sections, go through all of that, highlight where the structure is, highlight where your insulation is, and then look at any areas where those things cross particularly, but anything gets a bit tight. So then I've gone through and highlighted where those issues might be. I said where the junction where the steel frame is coming through to meet the concrete foundation through the insulation line. We've got that happening a couple of times. We've got a junction there where the timber frame's coming down and it's sat on the steel frame, but the steel frame's maybe slightly outside of where the timber frame line is. So we're just looking at those. So obviously this is a level of detail, sort of, that's probably a sort of 1 to 20, 25 section. And then you would be looking at that every time you go down a level of detail, so right down into all of the junctions, just to make sure that all of those things are being carried through into your detailing. And then we'll have a quick look at airtightness. So I don't need to explain about airtightness because other people have talked about that wonderfully already. But yes, build tight, ventilate right. And then for an image to add to everyone else's discussions on this, this is a visual representation of what the difference in air tightness targets are. So this is over an area of roughly 5 square meters. The allowable amount of holes for building regulations building would be that size of 5 20-pence pieces. And then for passive house, we're looking at just one hole of a 5-pence piece in 5 square meters. So it's just give you a rough idea of the scale and the impact that tricky tightness details can have, and you can quite easily get up to that level of holes through your structure, through your air barrier. And then just to sort of tie in with what we were doing earlier, similar thing with the air tightness, really, to look at where your junctions are, where your structure is in relation to your air tightness. This is the same as what the other guys have said earlier in the section and in plans as well. Drawing your air barrier with a red line, that's quite a common way to go about it. And then where your structure is in relation to that. Ideally, for detailing simplicity and just general sort of good practice, you either want your air tightness layer to be on the inside or on the outside of your structure, and all the same all the way around, which is particularly comes into consideration with retrofits, because sometimes you end up wanting to swap between inside and outside, or one thing on the existing building and one thing on any extensions. So I'd resist that temptation as much as possible, because it does make it very difficult to detail. Sometimes it's not possible, but it should be mostly possible. And in this instance, we've got the air tightness on the inside of the timber frame. So I've gone around, marked that up, and then we've got where our structure is in relation to all of that. And then we're just looking at junctions where that might be tricky to keep our air tightness on the inside of the structure all the way around. So we've got a couple of areas highlighted on this one here. So things like where you've got ridge beams or beams supporting rafters, there might be a junction where we've got maybe some air tightness membrane to go over the top of our beam before we install the rafters. So something about that, taping around the underside of beams gets very difficult and ugly. Where you've got floors coming into your walls, particularly where the air tightness layer is on the inside, that can be a tricky detail as well, that we got highlighted there. And then things like threshold details are always tricky for many things, like thermal bridging as well as air tightness, but thinking about how you might you might be able to keep that simple. And again, working up the level of details, thinking those things through all the way through your design process, working as a team to put it for the architects to put in input where the area is going to go, and then for the structural engineers to talk about how that links in with where the structure is. I think, keep talking together as a team, because that's how it gets sorted. And that is pretty much it. So key considerations: continuous air tightness, trying to keep a continuous layer of insulation all the way around so that we're thermal bridge free. And then obviously you're trying to keep you need to keep your structure contiguous as well, otherwise the forces aren't going to be transferred to the right places and it's going to fall down. So thanks.
That's brilliant, Beth. And
people to talk to.
Perfect. Yeah, I like that, Twitter people to talk to. What was I going to say? Completely went out of my head then. Utterly went out. So so you've really highlighted some good points, because this particular building, there will be external insulation on the front, internal insulation on the front, potentially external on the sides. So you've got that interesting corner detail to do, let alone up into the ceiling. And then if you decide to extend out the back, how do you make that contiguous and and also wrapping it around the into the floor zone?
Yes.
Really well said. Well, thank you very much. Have we got any questions? Because if we haven't, I will just wrap up, and we're off for a team building session with some of our participants. So obviously my scheduling is all back to front and upside down, and we didn't think that we'd have football on at the same time and all those interesting things that's going on, but that's life, isn't it? You know. Right, let me share screen and make sure I do the right one. So a huge thank you to Gervase, Florence and Beth. Go and follow them across LinkedIn, across Twitter, across blog posts. You know, you've heard directly from them. They have all been involved in Retrofit, and I would say you are the preeminent people in the country doing exactly what you're doing. And thank you so much for coming and sharing this knowledge, and hopefully sharing more of it as we go through. So this is, as Gervase calls it, the Wide Marsh Pavilion. So if you go onto the brief, you jump into the Google view or Google Earth. So we're looking at that triangle of land that the building sits on, and you can see here the the very shape of it, and you see the real height of it. Now you can't come beyond the front, but you can actually glaze in that front area. So that's going to potentially, a lot of air tightness in there. And then you can see from the old, from Britain from above, that it was next to the Bulmers cider factory, and that's where you used to all go out and play cricket. Good old days, you see. I know I'm old, but not quite that old. So tonight we're going to do some team formation, and then again tomorrow night, a little bit earlier, to do some team formation. And we'll carry on team forming until January. We've got spaces for up to 160 participants. That's 20 teams of 8. You'll come and watch all the recordings so that you can come and refer back to all of these. And software packages, so integrated software packages that all works together. So designing in SketchUp, you then import that into your design PH, and then with PHPP, which is the Passive House Planning package, the AECB Carbon Calculator comes as a PH ribbon that directly plugs into that. So in January, we will go into software workshops and distribute the software between you all. Where do you find the challenges? On the Timber Development UK website, which is the amalgamation of TRADA and the Timber Trade Federation. If you go on that particular page, you'll see some of the Southside Hereford has been updated, so you can see what last year's participants got involved in. And this is where we fit on our video channel. So Timber Development UK University Design Challenge holds all these webinars for you to go back and refer to, and obviously we can see the numbers rising, and I think that is my last slide. So thank you very much our speakers. Come and get involved if you're a student, whether you're architecture, engineer, architectural technology, project management, quantity surveying, landscape architecture, or any other built environment profession that we've forgotten to mention. Come and learn from the professionals what will probably be the most important jobs that you do throughout your careers. And with that, I'd like to say good night.